All right. All right. Here's our setup. We got the ramp right here. It's going to run along the track, go off the table, and just off the edge there, there's a target cup. The goal is to get it right into the target cup. Let's see if we can do it. Nice. Hear that sound? That's the sound of the ball going right into the cup. Why did it go right into the cup? Because of physics, of course. Oh yeah, physics. Now, let's take a more detailed look at what's going on. Here's like a side view of the ramp, as opposed to the above view. And here's the track. And then, by the way, here is the target cup. So you can see it is very high-end budget. It's a empty tomato can and a not-so-empty chili container. You don't want to eat that. That's some old chili. Okay, so the ball needs to start moving because the ramp rolls. The ball starts moving because the ball rolls down this ramp here, this ruler ramp. Okay, this means that for consistency, we always have to start the ball at the same height each time, or else it's just going to be junk, right? So you can imagine. Here, I'll put this stopper right here. If I start from up here, you heard it go. Now, if I start it down here, that's rolling for a much longer time. So now it's not good enough to just say, oh, I'll just always start it at the 9 right here. 9. Well, what if I don't have this set up here? What if I have to come after school and finish it? So it would be best if we just go ahead and measure this height. Measure the height, of course, it's going to be measured in centimeters. So that seems to be about 7 centimeters up. That's on mine. You do yours. But if we're starting from somewhere around here, we're going to get a nice consistent roll. And it doesn't really matter how steep this is, as long as the ball adequately rolls along nice and smoothly. If it's obviously if it's steep like this, that's going to just start bouncing instead of rolling. But notice that the starting height here is going to be completely independent of this length of the track here, as well as completely independent of the target height, as well as completely independent of how high up the table or the rolling surface is. Now, we want the ball to roll across the tabletop for as long as reasonably possible, going along here. Now, you'd say, why is that? And notice it's a full meter in length here. Why would we want it to roll as long as possible? Well, keep in mind, you would be timing how long it takes to go across. So once it hits here, rolling, and then toward the end there, well, right over there, just before it comes off of the table, you would stop the timer. So start the timer once it hits the table, and then stop the timer once it's about to go off the table. You're not allowed to let the ball go off the table unless I'm sitting there watching it and the cup is all set up and such. Now, why would we want as long as time as possible? Well, we are timing this, and we're using stopwatches, like the stopwatch on our phones, but it's still a stopwatch. And we know from earlier labs and activities that reaction time is going to be approximately 0.2 seconds. Now, that's 0.2 seconds starting here, as well as 0.2 seconds plus or minus ending here. So worst case scenario, we could be off by up to 0.4 seconds, worst case scenario. Well, if the ball is rolling for only half a second, being off by 0.4, if our measurement is 0.5 and our potential uncertainty is 0.4, that is bad news. Okay, but we don't want it to roll so long or for such a long time, such a large distance that the ball might actually be affected by the imperfections in the tabletop. So this is a nice happy medium. It's 1 meter going across, and that means it's very easy. We just measure how long it takes for the ball to go across here. Do that 10 times because you need repeated trials. And it's going to be about a second, give or take a little bit, but about a second. So you can easily figure out what the speed is going to be, the rolling, this rolling velocity, because we know the distance rolling is going to be 1 meter, and you are measuring the rolling time, the T rolling, or the trolling. Now, we've just gone ahead and talked about measuring our rolling time, and we also talked about measuring this starting height. Not that we're going to do any calculations with this, but we just want it for consistency. And we already talked about measuring our rolling distance. And to keep track of all this, here I have this lovely diagram right here. This is part 1, where we are rolling, where it's released from up here on this ramp. And then part 2, where it's rolling. This is the rolling section here. And then this section right here is where it's falling. Okay, so make sure you are distinguishing which distances are which, because are they likely to be the same? No, they're not. Okay, and in fact, let's start talking about these distances. So I have, let's see, I have my meter stick here, and I can measure the approximate height, and you would actually do this yourself in class. So you can see it's down on the floor there. This is going to be about 75 centimeters. About, it depends on the table. That might be 76, 77, something like that. Okay, so that is the height of the rolling of the table surface, the rolling height. Okay. Now, is that going to be the falling distance? Well, it does fall into the cup. So I do need to figure out information about the cup. To do that, I've got my cup here. And like I said, you'll be doing this measurement yourself in class. But it is approximately 22 or so centimeters tall. Of course, you would want to convert that into meters. And if you are interested, the diameter is about 7 centimeters. Once again, convert into meters and do those measurements yourself, because that's part of being a young scientist. Okay, so now we have all sorts of different measurements. You are making this measurement here of the height. This distance here should be a meter. You're measuring the time, the rolling time. Let's see, and then you need to go ahead and calculate the falling distance on the x-axis, as well as the falling distance on the y-axis. Well, that one is kind of measure and kind of calculate. It's really a combination of both, right? Okay. Now, our goal is to figure out how far away from the base of the table we're going to put our target cup. So our primary goal is this guy right here. Really, if you just think about this as a horizontal launch projectile motion problem from our homework, and we've already got a basic sketch, although you should make one yourself. If you go ahead and draw this out and label your sketch and make the lists and choose the equations and rearrange and calculate and such, you should pretty easily get your final answer. Why? Because of physics. Now, this is an introduction. It's a video introduction. If possible, I'd like to be able to do this in the classroom, but it's also good to be able, as in the classroom with you folks. But this is going to be a little bit more detailed, and you can go back to this and take some notes and watch and rewatch and stuff like that. But the goal is for you to make these measurements and calculations, and as I said, you're going to figure out where to place this cup so that it will have the ball go right into it. So is it going to be there? I don't know. Maybe it's going to be out here. Maybe it's going to be here. Okay. We have to figure those out, but you're not letting the ball go off of here unless I am standing directly over the ball, or directly over the cup. Okay, because otherwise that'd be like cheating, because then you can just kind of home your way in on it. And of course, if it goes off to the side, like if it lands there, I'd let you redo that one. Okay, but if it lands like right here, or in front or in back, then that's no good. We want it to land right in there. Not only do we want it to be successful hitting the target, but you also need to be able to explain the physics of what's going on. because you can just hit the target with luck. I'm much more interested, can you understand physics?